All right, let's get started. This is a much bigger crowd than I usually get in a security talk, which is interesting. The first slide in my talk, in fact, right, we're all not scared enough, is that usually is reflected by the fact that security talks, nobody comes to them, which is it's an interesting problem, right? Because security it becomes a more and more and more important part of all the applications that we do, and it's something that people think of less and less and less and less as time progresses. Is that a lot of the work that we do on a day-to-day basis is absolutely insecure. In fact, the move to the web, the move to things like microservices, so on and so forth, those are very difficult systems to secure. And people build them as if security is just simply not a factor. And that's actually, to me, really disturbing. We'll talk about some of the specific issues, but the general issue that people aren't thinking enough about how to make their systems secure is a big deal. This is particularly the case now that people are using technologies like HTTP to talk to servers, right? Because now it's possible for somebody who's a hacker to use our service API to get directly into a service that's running deep inside the data center and can do an enormous amount of damage if somebody breaks into it. And people aren't thinking about secure access when they put those kinds of systems together, so that's an issue. So what I'll be talking about in this session is security, not cryptography, two different topics. In other words, I'm going to talk specifically about what security means in the context of a computer system, and we'll talk a little bit, and when we get to the end of the talk, I have an example of a simple what hackers do when they hack into your system. But this is a kind of big picture talk, not a little picture talk. We're not going to talk about any security APIs or anything like that. We're going to talk about what security means and about how to secure your system. And I really want you, more than anything else, to start thinking about security issues. The problem is not going to go away. It just keeps getting worse and worse over time. And these statistics are now 10 years out of date. I've got to update this graph, obviously, but it keeps going, right? If you look at a contemporary one, it's just, you know, a hockey stick curve up the wazoo in terms of the number of exploits and the number of attacks that happen on systems on a daily basis. It's a given, is that when you put a new router online, somebody's going to be in your router within probably half a day. Is that somebody did a study of Windows machines, and if you take a Windows machine that's completely unsecured and put it onto the internet, just plug it onto the internet, you will have a hacker pinging it within 5 minutes. So you talk about communication in secure ways. Literally every telephony switch in the world has hacker software in it. Because people have hacked into the actual switches and they're in control of the network. So we have to assume that we are living in a hostile world with respect to the security infrastructure. Is that there is no way that you can get outside of a computer and have a secure system. Is there? Well, there's one way. There's absolutely one way to give you 100% security on any computer system. What you do is you walk over to the wall and unplug it. That's your option. Since we can't do that, we've got to be thinking about the issues here. So launching attacks is easy, right? Is that and it gets easier and easier by the moment. And as I mentioned a moment ago, web services are particularly vulnerable to these kinds of problems because you're accessing them across the web. Even when you're accessing them within the data center, they're vulnerable to problems. The bigger the systems, the easier they are to attack. But I think the most important issue is that bottom one. Is that a lot of the issues that have to do with actually securing systems are relatively easy problems to solve. Is the biggest entry point into server systems still is something called SQL injection, which I'll talk about at the end of the session. And SQL injection is one of the most well understood attacks on the planet. We have known about it ever since the internet existed. And we know how to solve it. In fact, solving SQL injection is trivial. But a lot of programmers don't even know what SQL injection is. How many of you do know, just out of curiosity? Oh, most of you. That's surprising. Is mostly when I ask that question, maybe half of the people in the room will raise their hand. But how many of you who know what it is are actually taking active steps to protect it against it in every program you write? Maybe 30% of the people that raise their hand knowing about it. So that's the problem. Right? All of the rest of you have vulnerable systems. And it's because writing systems that are secure is hard. It's extra work. Gets in the way of that schedule I was talking about in the keynote, right? Is that people say, I've got to get stuff done on time, I can't be thinking about security. The main issue though is that having an absolutely secure system isn't necessarily desirable. Is that what we're really trying to do here is balance two conflicting needs. One is the need to have the system secure, and the other one is the need not to spend money. In other words, security is all about a balance between risk and liability. If the cost of the system being broken into is lower than the cost of making the system invulnerable, then leave it vulnerable. Credit cards operate under this model. Is that there's a lot of identity theft in the United States, a lot of people that steal credit card numbers and masquerade as other people, which of course is devastating to the person whose identity is stolen. But the credit card companies don't care. And the reason they don't care is because they've run the numbers, and they found that even if they pay all of the bills of all of the people whose credit cards have been stolen or whose identities have been stolen, that would still cost less than making their system secure. So rather than spend the money making the system secure, they'd rather pay those bills. And that doesn't help us much as consumers, but that's the equation, that's the calculus that people go through, is that it's all really about risk and liability, and it's all really about legal infrastructure more than anything else. In other words, what matters is not so much whether the system is secure as the legal framework within which you're using the system. Or put it another way, people worry about Google, right? At least in Berkeley where I live, is people they treat Google as if it's a creature of darkness. And who's going to steal all your data is that I guess the NSA has eclipsed Google at this point, so they have something bigger to worry about. But the issue with Google is that if you sign up for Google Apps, get a Google Apps account, they have a contract that says we're not going to snoop around in your data. Well, that's a better protection than any kind of technical security would give you. In other words, you could make your system secure, but no matter how you make it secure, somebody's going to break that security. On the other hand, if Google breaks the security, you can sue them for a lot of money, and they worry about that. So the fact that there's a contract in place actually does more to keep your data secure in the Google ecosystem than any kind of security infrastructure you could put on top of your own data, any kind of encryption you could do on top of your own data. Is that contracts are important, in other words. Because this is really not just a technology issue. It's hard to do. This is all kind of stuff that I was talking about, right? It's people don't understand how to do it. Unfortunately, one of the problems with security APIs is that security APIs are all written by guys that are into cryptography. People who are into cryptography are into codes and ciphers, which means they design their APIs to look like codes and ciphers, which means it's almost impossible to program to them because they all are codes and ciphers, because we have to spend a lot of time studying them and trying to figure out how they work. Alphabet soups full of algorithm names that none of us understand, and complicated mechanisms, overcomplicated mechanisms, I would argue. In other words, the mindset that goes into being a security guy or being a cryptography guy is working against us as programmers here, which makes it hard to do, which again is something that's in the way of having the system actually be secure, is that it's hard to do. I just talked about the legal stuff. The other issue is that people tend to not think about other people as being human beings. Social attacks are the biggest kinds of attacks that happen on systems. In other words, the easiest way to get somebody's password is to get on the phone to tech support and get the password, or at least get the password to be changed. If any of you are not doing this, by the way, there are some places that have to be more secure than others. So your email account is the key point of vulnerability in your personal life. So if your email account is not absolutely secure, you need to go home right after this day and get it secure. So if you're using Gmail, for example, you must be using two-part authentication. You should be using a separate authenticator in order to get access to the account. The reason for that is that if I want to break into your account, what I'll do is I'll call customer service, and what they'll say is, we'll email you a reset password. So if I have access to your email account, I can get access to every other account you have because I can go through the lost password mechanism on everything that you do and have an email sent that will allow me to reset your password to something that I know. So if your email account is vulnerable, everything is vulnerable. And that's a classic problem in the security world, is that one point of vulnerability opens up the entire system. I'm going to actually give it a minute, which I shouldn't do, but I'm going to, based on our prior experience. Unfortunately, most people who die in hotel fires, the reason they die is the fire alarm goes off, and they open their door and they look out in the hallway, and what they see is a whole hallway of people that have just opened their door and they're looking out in the hallway. And since nobody's actually leaving the building, they all just close their door and go back into their rooms and they die. So ignoring a fire alarm is not a good thing. A fire alarm, rather, is not a good thing to do. But anyway, we get back to this notion of people, right, is that often programmers make assumptions, or they hold in contempt the users of their systems for not doing things that seem obvious to them, right? What an idiot, he clicked on this link. Well, it's perfectly reasonable for a normal human being to click on a link that comes in an email that appears to be coming from somebody they know, right? It takes a certain amount of paranoia to not do that. And you can't really expect people to not do that. So our whole password-based infrastructure is vulnerable because programmer types have said, well, if you're so stupid that you're going to give your password away, or if you're so stupid that you're going to have a password that people can guess. You know, somebody did a study of the University of California passwords. This was a long time ago now, 20 years ago now. But what they found was that 95% of the passwords in the UC system were one of the 5 main characters in the Lord of the Rings. So you go through Frodo and Bilbo and Gandalf and you're in, right? Is that it didn't take long. And it was because the passwords weren't secure, as people weren't thinking about that. But of course, the people in charge of those systems were thinking, who could be dumb enough to do that to use that as a password? So you can't expect people to be behaving in ways that work from a security point of view. The other issue is that people worry about the wrong things. Is that I still know people who won't do business on the internet because they're afraid of having their credit card stolen on the internet. Well, believe me, there is no hacker sitting at their telephone like in a 50s movie monitoring internet traffic and stealing passwords as they move across the internet, or stealing credit card numbers as they move across the internet. We could all do credit card transactions all day sending our credit card numbers across unsecured lines, and it wouldn't matter. Because what hackers do is they break into the businesses and they harvest 100,000 credit card numbers in one chunk, right? They're not monitoring stuff over the wire, but people worry about the credit card number moving over the wire. So that, of course, is the Security Programmer Full-Time Employment Act, which is a good thing, because it means that we have to add the security theater to our applications in order for people to think that they are more secure. But simply adding a password or adding SSL or something like that is typically not going to make an application more secure. I can hack into your app over a HTTPS connection just as easily as I can hack into your app over an unsecured connection. But if it doesn't have that HTTPS there, people don't feel like it's secure. So you have to go through the trouble of putting it in there. Now, the biggest problem, I think, has to do with people imagining that security is about the perimeter. Is that a lot of systems are vulnerable because all of the security is done in the perimeter. Is that big corporate systems, for example, that have many layers of firewalls to the outside, and you've got to do everything through proxies. And once you get inside, though, there's no security at all. And the issue is that people imagine that what we've got is that, but what we really have is Imagine-O-Line. In other words, there is no way to fully secure the perimeter of any organization from a security point of view. There's always some point of vulnerability, some Belgium, that you can use to get around the perimeter, whatever that perimeter is. So this notion of we can make internal systems where we don't have to worry about security because people can't get through our corporate firewall, that's a really dangerous way of thinking. Is that people can easily get through your corporate firewall. That is just not a problem. And they can do that from anything from physical means, which is to say they could drive up next to the building and open up a computer that's got a Wi-Fi connection and hack into your Wi-Fi system. Or they could hack in more traditional ways using some kind of virus or worm or something that would get into the system electronically. But the point is that imagining that by making the perimeter secure that you could secure everything else, that's a false sense of security. You can't do that. So rule number one then is that everything has to be secure at every level. You can't stop checking things simply because you are in the system. You can't check an access token at the web server and then stop checking that access token at the internal service that the web server is using. right? You have to have security all the way through. It has to be pervasive from front to back. The other problem is that people think about security in terms of penetration testing. Is what they're going to do is they're going to hire somebody to attack the site. The problem with hiring somebody to attack your site is that what they're going to use to attack it are known exploits. Typically, they have programs that people write that just attack the sites, right? That run through every exploit, every known exploit systematically and try and get into the system. The problem are the so-called zero-day exploits, or the ones that allow you to, or the ones that nobody knows about, the things that somebody just discovered. Which is to say, if you're talking about penetration testing, if you're talking about somebody saying, you're secure because I can't break in, the scale goes from don't know to I'm in deep trouble. There's no point on this scale where there is I'm secure. In other words, if you cannot get in with any known attack, then you don't know whether you're secure or not because of all the zero-day exploits. If you can get in with a known attack, you're in deep trouble. So these have some value, but the notion of having some kind of external analysis, some company looking at your system and telling you that it's secure, that's a very limited assurance. Is that it's better that it's worth doing, right? Is that because you would like to know if you're on the deep trouble side of the scale. But it's not going to get you into the I don't have anything to worry about side of the scale. People also spend too much time doing things like relying about firewalls. In other words, if you think about firewalls, the whole firewall notion is based on the idea of blocking ports. And historically, what happened then is that you needed to write a program that was accessible from outside of your server. So you wanted to get onto a TCP IP port in order to do that. You went to the guy with the keys and the cop hat over in the IT department and said, I need a port and a firewall to use for my program. And they said, oh God, we can't do that. We can't possibly open up a port for you. So programmers are programmers. What we did is hacked into our own computers. In other words, right now, everything that you can do through port 80. Because port 80 is always open, right? The web server is always open. So in other words, what these IT guys did is forced us to be hackers in order to be able to get work done. So at this point, the notion of a firewall has become almost meaningless because it doesn't matter whether the ports are open or closed as people are going to get in through known ports. And they're particularly going to get in through ports that access programs that we write, which is almost always port 80. It's almost always the web port. So the firewall is not achieving any purpose. The only way for the firewall to achieve its stated purpose is to shut down port 80, in which case all of your web activity would stop. So that's not going to happen. The other issue is that firewalls don't protect against things like denial of service attacks. In other words, a denial of service attack is a situation where somebody is loading your system so much that it ceases to function. However, if you have a denial of service attack, it's not really getting into, nor does it need to get into the system. In other words, you can break somebody's system from a business point of view without ever actually breaking into the system. All that you have to do is make the environment around that system so busy that none of your customers can get in either. So you're vulnerable even if your system is secure. So this whole idea of securing the application from the outside, it's just misguided. It's that we have to be thinking about secure at every level, but more to the point, we have to be thinking beyond the application if we're thinking about actually securing our systems. So a classic example of that is sound, right? As iTunes came out with its original, this is an older slide, but I've kept that up here because it demonstrates the problem, is that iTunes came out with all this DRM. Right, is that we're going to secure music delivery. And what they weren't thinking is that underneath iTunes, there's a sound driver, there's a sound card, there's a digital output from the computer if worse comes to worse. And all of those layers are vulnerable. Right, if you think about all of the capture programs that you use now, right, is that you want to grab a video off of off of YouTube, or you want to grab some piece of sound that's being streamed on Spotify, you get something below the application to do that, something that links into at the operating system level to grab the digital stream. It's digits are digits, as you don't lose any any quality simply by going down to the driver level in order to steal stuff. So again, here we have an application that thinks of itself as secure, but the problem is that it is made vulnerable, by the surrounding context. Right? Now, the solution in the case of music is to just use a CD, right? In other words, you just distribute it on some medium that is not easily duplicated. But with most computer systems, we really can't pull that out because the surrounding context is too big. And there's a lot of scary context here. You know, here's my app. Well, how do we know that the operating system is not vulnerable? It probably is. You know, people pretend that the Mac OS is not, but of course it is. And Windows obviously is vulnerable. The file system itself is a point of vulnerability, as people can put things on the file system that could damage your program as the program is working. The compilation environment, right? Eclipse, for example, or any of the open source compilation environments, but even the non-open source ones like Visual Studio, you plug stuff in all the time. Can you guarantee that those plugins are not stealing your source code? Can you guarantee that those plugins are not injecting viruses into your code that you can't see as part of the compilation process? Can you guarantee that your compiler is not emitting code that has had a virus added to it? In other words, you can have a virus put into your code without you knowing it. It's not in your source code, but the compiler can modify things at the binary level to make your system vulnerable. Right? None of us can do this. How many of you actually check all those long checksums that come down when you install a piece of open source software? Nobody ever checks that stuff. So how do you know that what you've loaded is actually what you think you've loaded? You don't. But you use it. So what's it doing to the systems that we're putting together? Who knows? Is everyone following me here? You know, other simple, the registry, right, is that I don't know how many programs go from demo mode to real mode by flipping a bit in the registry. Gosh, that's secure, right? But again, these are all things that are outside of our system. Other issues. This one is particularly interesting. In other words, what we're having here is equipment that has hardware in it that is violating our security. Is everyone following me here? I don't know how many people know that the Xbox, you know the little camera thing that's on the Xbox that sees where you are when you're dancing around? How many of you know that for almost 2 years, that camera was on 24 hours a day? And it was actually broadcasting a picture of what was in that room to somebody outside of your house 24 hours a day? So that people could see everything that happened inside that room if you happened to walk into the room that had your Xbox camera in it? One of you knows that. Scary, isn't it? You know, it's big. That really is Big Brother. Right? Is that we're not thinking about the right things, right? The compiler, right? I did mention the compiler. The compiler is the big one, right? Is how do you verify that your compiler is not injecting viruses into your system? Of course, nothing on the web is trustworthy. So anything you get off the web is not trustworthy. If no matter how you download it, if you're downloading it with RPM or whether you're downloading it with Homebrew or whether you're downloading it just by clicking on a link, you have no idea what you're actually getting. Checking those checksums is important, but nobody does it. I don't do it. I ought to, but I don't do it either, as I just have given up on this particular issue. But if you haven't figured this out yet, security people are really paranoid. Is they worry about lots of stuff all the time, because every place you look, you see vulnerabilities. Now, the other issue to think about here is that the way that hacks work is they're all taking advantage, all attacks take advantage of some kind of bug. And all software has bugs in it. So all software is vulnerable at some level. Now, some of those problems we can address easily and some of them we cannot address easily. But the real lesson here is the most important thing that you can do to make your systems less vulnerable is to test them adequately. Extensive testing. Lots and lots of unit tests, lots and lots of outside tests, stress tests, everything that you can possibly think of. Because it's the bugs that are going to make the system vulnerable. Nobody deliberately puts holes in their system. So one of the places where things go wrong is that a company who's worried about security will not increase the size of its testing staff by a factor of 2 or 3, which is what it really needs to do to get security. Instead, they'll bring in expensive security consultants to analyze architecture and that kind of stuff, and that's not going to help. Testing is going to do more than anything else in terms of making the system secure because it's going to address the bug problem. The language really matters too. For example, C and C++ is extremely vulnerable. Is that we've all heard about buffer overflow problems. Does everyone know how a buffer overflow attack works? Does anyone know? If you know how a buffer overflow attacks, raise your hand. All right, it's a small enough number that I should explain it. The way that a computer works, deep down inside the chip, is there's a stack, right, data structure, the stack. And that stack holds lots of information. Now, when you call a function, what happens is that there are several push operations that push the arguments onto the stack. And then the function is called, and as a side effect of the function call, the return address of the function, the place to go when you hit the return statement, is pushed onto the stack. And then space is allocated on the stack for local variables. That whole thing is called a stack frame. Now the problem is that when the function returns, what the code is going to do, the assembly language level, is it's going to go down to that return address and jump there. So the code control will transfer to wherever that return address is. But bear in mind that below that return address are all the arguments, and above that return address are all of the local variables and so forth. Right? Now, usually stacks grow down as 0 is in this direction. Okay, so everyone following me so far? All right, now, imagine that you read a really long string from input, or you pulled a file off the disk, and you didn't check the length of the thing before you put it into a local variable. Right? Well, that means that the length of the thing, again, we have local variables, we have arguments, we have that return value. If the local variable space is artificially extended down into the return address, it can actually overwrite the return address of the function. Is everyone with me here? So if you have an array up here in the local variable space and you don't do array boundary checking when you start putting things into the array, you're putting things into the array, you hit the end of the array and you don't check and you keep going, eventually you're going to hit that return address and overwrite the return address. Now, if this is just a bug, the symptom will be that the function, this is just a bug, the way that the system is going to, what'll happen is the system will just blow up when you try and return, right? You'll get a seg fault and the debugger will give you a breakpoint and you're off and running. But if this is a program that's actually functioning, that's been attacked deliberately by somebody who knows that there's a vulnerability. In other words, the hacker knows that the array is 2K. And the hacker knows that 18 bytes or 16 bytes below that 2K limit is the return address. The hacker can give you a file that has some executable code on it that deliberately overflows the buffer and overwrites the return address with the jump location of the beginning of their executable code, and you're off and running. That's a buffer overflow attack. All right, now to do that, you need to be working in a language that doesn't check array boundaries, which is to say C or C++. Or if you're in the Apple world, Objective-C does not check either. Which means that simply writing the program in that language has made you vulnerable. If you're working in a VM kind of language, Java or any of the JVM languages or C#, any of the CLR-hosted languages, you're safe because the CLR or the JVM or whatever the virtual machine is checking array boundaries for you. So the language matters. Is everyone following me here? By the same token, true interpretive languages like Ruby or Python, those are inherently more vulnerable because the source code can be changed dynamically as the program is running. So you've got to be thinking about the language. Other simple things that you don't think about, right, is that here in C++, for example, this is a basic stack overflow, right? Is gets, which gets a string from input, does not check lengths. So it can easily overwrite that 128-bit array that that's the example I was just talking about. But even in Java, right, you look at Java, here we're getting a password from a user and putting it into a string. What's the lifetime of that string in core memory? Any other inputs? It's indefinite. You don't turn your server off, it could be there a week later or a month later. The lifetime of that string is until somebody overwrites it with a different value. And somebody could be the current program, but it might not be, because that string might be copied out to virtual memory, which is a file on the disk. And if nobody else allocates that particular chunk of virtual memory in the next year, then that password will not only exist in memory, but it will exist in your disk file system inside your virtual memory files. Everyone following what I'm saying here? See, Sharp obviously has the same problem. Right? So there are vulnerabilities in the language that we don't think about when we're programming, right? It's that somebody who's thinking about this kind of stuff won't ever put a password into a string object like this. They'll put it into an array of bytes, and they will zero out that array as soon as they're done with it. And even that's not perfect, but it's way better. The 2010 attack on Google was kind of interesting. Invalid pointer reference, right? Here we're back to a language problem, right? It was a pointer that was pointing at the wrong place. It's bugs. The point I'm trying to make is that this is all bugs. And it's all bugs that are caused by vulnerabilities that are implicit in the languages that we work in. Now, the difficulty there is that the ratio of bugs is a direct function of the code size. The bigger the code, the more bugs it has in it, so the more vulnerable it is. Again, I got some statistics for some old operating systems. They stopped publishing these after a while, so I can't update the table, but I can't imagine that any of the Microsoft operating systems are getting smaller over time. And certainly Linux is getting bigger. Linux had an advantage over Windows for a while because it was much smaller, but that's changing. So the bigger the program, the more vulnerable it's going to be, because bugs are a function of code size. Which is a good argument for microservices, right? Is that it keeps the code size smaller on the individual services at least. Static analysis is one useful technique that you can use to address this problem. In other words, you can buy programs who analyze your source code looking for security problems. So they'll look for the obvious things like buffer overflows and that sort of stuff, but they'll look for subtle things too. So static analysis is not a bad tool. It's not going to find all of your problems, but it will, among other things, find bugs for you, because often the things that it's finding that are making your program unsecure also happen to be bugs. Even something simple like lint can help find simple bugs if you're working in the C++ or world where tools like lint exist. Crypto is not going to help. Magic crypto fairy dust is the tool that a friend of mine uses, right? If we're gonna wave our magic crypto fairy dust wand, and all of a sudden things will be secure, because all that does is secure the transport, right? As if SSL itself has security vulnerabilities in it, but over and above that, we have the problem of anybody, if the bad guy establishes the connection, it doesn't matter whether or not the connection is secure. Making it secure, all that means is that two bad guys can't be attacking you at the same time. You can only be attacked by one bad guy. So crypto is not going to help much here. No amount of SSL and so forth is going to help us much here. One of the best examples is does anybody have a Apple power supply? I am losing my battery, and I left my power supply upstairs. Nobody. Can I borrow it for the remainder of the session? Thank you so much. It's a laptop. Oh, you don't? We might have to take about a 3-minute break so I can run upstairs and get my power supply. They were going to bring it down and you didn't do it. But let's talk about well, look at this comment, right? Is that the crypto nerd is imagining all sorts of bizarre stuff in terms of attacks here, and you're thinking about SSL and, RSA encryption and yada, yada, yada. And meanwhile, the actual bad guy here says, I'm going to hit him over the head with a wrench, right? Again, we're not thinking about the right things. Security also has nothing to do with, oh, good, you have saved my life. Please remember to get it back. Oh, it's one of the old ones. It's not going to work. All right. We're going to have to take a 2-minute break in about a minute. But where was I? Secrecy is not going to help here either. Right? In other words, a lot of people think they can do without the cryptography by making things secret. A lot of people think they can make up their own cryptography systems. They can make up ways of hiding stuff, and that somehow their system is going to be better than an official crypto system because nobody knows how it works. And I can guarantee that that point of view is not going to help you, is that amateurly built crypto systems are extremely vulnerable. They're always extremely vulnerable. There's nothing that you can do that's going to work as well-known crypto algorithms that have been studied assiduously by a stack of 500 mathematicians who have proved that they're vulnerable or not. Crypto does buy you some useful things, though. It buys you the notion of access control, for example. It can give you some control over who can access your system. It can give you confidentiality in the sense that you can talk to some system without that system knowing who's doing the talking. It can give you authentication in the sense that you can prove to some remote system that you are who you say you are. It can give you non-repudiation, which is to say the remote system can say, you logged on at this time, I can prove it. And it can give you integrity in the sense that when you send something across the wire, you know that the thing that you sent is the thing that you sent. The thing you received is the thing that got sent. And those are all valuable things. So I'm not saying that crypto is not worth knowing about because it gives you these advantages. But it is it's not a secure end-all. It's not just going to give you, it's not going to make things secure. Now, the other issue is it breakable or not? In other words, when you start talking about cryptography, then the real question is how long is it going to take to break it, not is it invulnerable? Is everyone following what I just said? All crypto systems can be broken. It's just a matter of how long. In the example here, you've got a 4-wheel combination lock that has 10,000 possibilities on it. If you try one every 2 seconds, it's going to take you 5 hours to break the system. If you have two locks with identical combinations, it's going to take you 2.5 hours if 2 people are working blocks, because they can divide and conquer. They can each try half the combination. 4 people, of course, can give us another divide by 2. If you have 10,000 people, it only takes 1 try per person. So if you have enough computers working on the problem, you can break any crypto system. It's just a matter of how long. So the question then becomes not, is this document hidden forever? But rather, is this document hidden until such a time where it's not valuable anymore, where it doesn't matter if somebody knows what's in it? Everyone hear what I'm saying? You know, the contract, for example, if you can't break it for 10 years and it's a 5-year contract, fine. I don't care if you break it after the contract expires. Okay? So really what we're talking about here is cost. Is that it's expensive to break through a crypto system. If you're the NSA, you can do it because you've got infinite funds just about. If you are us, you can't. So really what we're just talking about is money. The more money you have, the easier it is to break into the system. So if you're doing corporate stuff where security is important and your enemies are other large corporations, they have the money. If your enemies are some high school kid working out of his den, then you don't. Then he doesn't. You don't have to worry as much about him. All right? But that said, you should still be using HTTPS every place. All right, any questions? Okay, now that I've whipped this all into a frenzy, I have to get a battery or this is going to just die, and we're at a good stopping point. So if everyone wouldn't mind taking about a 2-minute break, I'm going to run upstairs and get my power supply and come back down, and we will continue this.
Now, we're not sure what time they break for lunch, but we will start it from then and we will decide how long it's going to work.
Oh, good. He was going to bring it down to me. That is definitely mine. Thank you. Thank you so much. All right. Oops. Okay, let us carry on. So let's talk about how we're going to try and make some attempts at least to resolve these problems. The first big problem is that we need to get the business guys to care. Now, more and more, they do care, but they don't care about the right things. In other words, they see companies in the US, for example, like Target, getting broken into and having 1 million credit cards stolen. But they worry about that, but they don't know exactly how to deal with that on a day-to-day basis with the systems that they themselves are paying to be produced. In other words, everything is a cost-benefit trade-off as far as the business guy is concerned. So all of us worry about security inside our systems, but often the business guys just simply don't worry about them. So what we have to do then, in order to make them care, is make a business case for making the system secure. And I should say this applies, I'm going to give you general advice. I've got to put on my daddy hat here for a second, is that I do a lot of consulting in the Agile space. And the biggest problem I find in the Agile space is that the C-levels in the company, the guys that are way up at the top, do not understand what Agile is. They think it's just some process that the engineers use. They think that Agile is just about stand-up meetings and that kind of junk. And they imagine that they can bring in some trainers who will train people on Scrum, and voila, the company will be Agile. Now, the problem, I think, is not just their problem, but it's also our problem, because we're not explaining what Agile means to them adequately. And the difficulty is one that I'm about to talk about in the context of security, which is when a CEO asks somebody in the organization to explain Agile, What that person will do 9 times out of 10 is to start talking about stand-up meetings and backlogs and process stuff, which makes no sense at all to a CEO. His eyes will glaze over within 15 seconds, and that will be the end of it. You will never get another chance. What you need to make Agile work inside your organization is to convince the person who's making the decisions that there is business value in agility. And this has nothing to do with process. This all is about business. This is all about increased profits. If you cannot demonstrate that Agile is going to affect the bottom line, you will not make a good case for Agile. Because all these guys care about is that bottom line. That's their job. It's a CEO's job to control the finances of the company, ultimately, to control the profits and losses of the company. So you have to prove that there's some advantage to doing Agile. And there's lots of ways that you can approach that. You can approach it from the cost of producing software point of view. You can approach it from the, we can produce products that are more valuable for the customer, therefore our sales will go up point of view. We can attach it from the risk analysis point of view, is that doing things in an Agile way is less risky than doing things in a traditional way. Therefore, you can plan more effectively. We can approach it from a planning point of view. We can say you can plan more effectively. Is that here are projections that you can make. Those projections I was talking about this morning in the keynote, those are important projections to be able to make at the CEO level, but are very difficult to make if you're not doing things in an Agile way. But that's the point that's going to get their attention. Is talking about process is not going to get anybody's attention. Now, the same applies with security. Is we can talk about vulnerabilities and this and that until we're green, and it's not going to make anybody put any more money into making the system secure. What's going to get them to put money into security is by providing a business case for that. Is that if we are broken in because of this vulnerability, we are going to lose this many million pounds within the next year. And it's going to cost us 100,000 pounds to fix it, but we're going to lose $1 million. What do you want to do here? Right? It all comes down to money. So we have to start getting into the habits as programmers to making a business case that business guys can understand. We have to think about business risk. We have to think about how we're going to tell whether we're vulnerable or not. We have to think about probabilities, as what's the likelihood of being attacked in a certain way? What impact will it have on a company? And more importantly, what's it going to cost us? Now, we can do this, right? We're all smart guys. We all know math. But we often don't. So the first thing that you need to do as a programmer in order to get your systems more secure is to convince the uppity-ups that they need to put the money into it that will make it secure, and the way you do that is by making a business case. All right, so that's step one then, in terms of making our systems secure, is we want to convince the boss that it's worthwhile to have them secure. Then we want to start looking at the way that we make the code. Is that we want to create secure systems by eliminating as many bugs as we can with things like code reviews. I should add to this, this is a list that came from one of Gary McGraw's books. Gary is actually one of the better writers on security if you want to investigate him. And on Amazon, is that he's written probably half a dozen books at this point on security. But he actually wrote this list before Agile was popular, so I would add pair programming to the #1 position. Pair programming is an on-the-spot code review. When you're doing pair programming, you have two people writing code at the same time. So effectively, the way you can look at that is one person's writing the code and the other person is doing a code review as you're writing. So I think pair programming is even more effective than formal code reviews because the bugs get fixed very, very quickly and they get identified very quickly. And 100% of your code is subject to code review because if you do everything with pairs, there's always a second pair of eyeballs looking at it. Other Agile practices like constant refactoring, it's the same issue, is that if you have a culture of refactoring within your organization, it will do the equivalent of code reviews. It will be finding bugs and fixing them. Doing architectural analysis is important. Is that a lot of times, particularly in Agile shops, people lose track of what the architecture looks like, and it's good to have a person around that whose job is to just keep the big picture. It helps a bit in the security situation that we're talking about, in that problems won't leak into other parts of the system through the database. But I can't do a security audit for you sitting here, but that's a very vulnerable system you're describing.
I mean, it's a case of like, I'm isolating security, which I did for a few years.
Yeah.
There's no such thing as
Yeah.
best effort.
Yeah.
And
Yeah. Yeah.
I have two things. One is about storing password in some languages. On the beginning of your lecture was how this is stored in the memory in C++ and Java, and this is in the memory in clear string. And I think that even for this Java, C# and other good languages, it is still set in the memory in clear form.
Yeah.
So this is not solving this
Well,
issue, but there is something in C# called secure string, which is all the time encrypted.
it's not encrypted all the time. It's just plain for a very short time. There's always going to be a plain text version somewhere for some amount of time. It might only be microseconds, but it will be there for some amount of time. There's always a point of vulnerability. Now, with normal passwords, as soon as you get a password, the first thing you should do is hash it, right? I said I wasn't going to talk about crypto technology, but a hashing is a secure hash is pretty much a unique number. In other words, every string produces a unique fingerprint, if you will. And changing as much as 1 byte in a really long string will change half of the bits in the hash. And no two strings will hash to the same value. Now, that last thing is not a guarantee, but the odds of different strings hashing to the same value are very, very small. So when you get a password, the first thing you should do is hash it and store the hash. And then when you get somebody logging in, the first thing you do is hash it again. And then what you compare are the hashes, not the passwords. But there's that moment in there where it's clear, right? So the only way around that would be to do the hashing on the browser side, which is doable. And there are some systems that go through the trouble of doing that, and I'm all in favor of that. In other words, nowadays you can buy crypto libraries that run in JavaScript on the browser. So you can do an SHA hash or something like that in JavaScript browser side and actually send the hash password up. All right, now there are still vulnerabilities there though, right? You better be doing that across a secure channel, for example. It's, the difference between sending a hash password and sending a plain password doesn't matter if you're trying to do a password attack on a system, but there's almost always a point of vulnerability. You're just playing the odds. You're trying to reduce the odds of attack by making the window smaller. And even with the Microsoft stuff, right, at some point, you have to convert the unsecure string to the secure string. And so there is a point of vulnerability in there when it does that.
And the second thing is about memory leak, which I don't see during this lecture anything about memory leak, but I think that this is also quite big security problem.
Well, the memory leak problem is really a variant on the buffer overflow problem, right? Except that now with the buffer that we're overflowing is the main memory store. Right, and but more to the point, if your only goal is to bring down the system, if you can identify a way to trigger a memory leak inside the system, then you can bring it down because eventually it'll take up so much memory that the operating system will kill it, right? So but that's not a special case though. It's just another bug, right? The reason a memory leak is a bug, and it's a bug whether or not you're talking about security. So getting back to something I was talking about earlier. The one thing that you can do to make your system more secure that's better than anything else is get rid of the bugs, is make it as high quality as you possibly can. So doing things like test-driven development, doing things like really formal testing, doing things like writing the code or the test before you write the code, doing things like making testing an integral part of your process. Those all will make your system secure because they'll find things like memory leaks. Right? So that's not a security problem, it's just a bug problem, but bugs are a security problem. So that's where we have to address things, is to take a step back and improve the quality of our system. Okay, anything else? All right, well, let's go upstairs and get some lunch, I guess. It will be a little bit early, but that means the lines will be shorter. And I'll be around for questions if you have more questions.